Okay, as promised, here is the follow-up recording, or the rest of the respiratory system lecture. And we have to talk. We got up to the point in class, in the regular class, where I am on the screen. Yes, I am. Okay, I want to make sure that I am there. We got up to in the rest of the class. We got up to the point where now we have to talk about gas exchange. Gas exchange either across the alveolar membrane or across cell membranes in other parts of the body in order to allow oxygen and carbon dioxide to do their thing. So cell membranes are permeable to these gases. Remember that carbon dioxide is nonpolar and oxygen is nonpolar, and cell membranes are nonpolar, and so carbon dioxide and oxygen just slide right across that membrane, which is nice. But the thinner it is, the better. Molecules diffuse from regions of high concentration to lower concentration, or higher pressure, or higher partial pressure, because they are gases. So higher partial pressure to areas of lower partial pressure, or higher concentration to lower concentration, etc. To determine the direction of diffusion, you just have to know the concentration gradient. It doesn't have to be a huge concentration gradient, it just has to be a difference. Alright, in the process of respiration, gases diffuse from high partial pressure to lower partial pressure. I want to make sure you understand this process. Now, because these membranes are thin, this happens very rapidly. And as I say, the thinner the better. And the more rapidly you can come to some sort of an equilibration, or you can get oxygen where you want it to go, which is bound to hemoglobin. And carbon dioxide has a number of ways that it can get around the body. And we're going to talk about that. So, more surface area, more diffusion. That's why lungs have millions and millions of alveoli. The more alveoli you have, the more surface area you have, the more diffusion you get. The steeper the concentration gradients, things go faster along the concentration gradient. If the higher concentration is really high or the lower concentration is really low, if that difference is great, diffusion goes faster. Now, of course, in disease states, you get thicker, you have the same thin membranes, but then you may have inflammation, or you may have, some sort of fluid buildup, and that makes the distance longer, and so it's harder to get things across a thicker barrier. Come on, how do I? Here we go, yay! It changed slides. Great. I'm going to get my little laser pointer thing. I love my laser pointer. Okay, so this is the inside of an alveolus. What you're looking at right here, there it is, alveolus. So we are where air has made it down. And of course, as I mentioned too, air has nitrogen in it. Big deal, you don't care. Your body doesn't care about nitrogen. It ignores it. Nitrogen certainly passes across this barrier too, but it doesn't matter. What matters is oxygen. The partial pressure of oxygen and the partial pressure of carbon dioxide. Those are the things we're going to focus on. All right, now the diffusion of oxygen. Once oxygen gets down to the level of the alveolus, remember that oxygen is 21% of air. And so when we did the math, we saw that there was a pressure due to oxygen at sea level, of course, but the pressure due to oxygen is 160 millimeters of mercury. It turns out that once it gets into the alveolus and all the way down in there, that partial pressure is actually diminished. And there are several factors that get in, that have a say in that. But let's suffice to say that once it gets into the alveolus, where it's going to diffuse, the partial pressure of oxygen has diminished to 104 millimeters of mercury at that point. So we're going to take that as our starting number. Okay? So this is in the alveolus. Well, of course, this is going to be right by a capillary where blood's flowing by. And remember, this is deoxygenated blood that came from the right side of the heart. which came from body tissues. So you get to review that whole process. This deoxygenated blood flows past the alveolus. Deoxygenated blood, on average, has about 40 millimeters of mercury partial pressure of oxygen. Here's our gradient. Okay, we have a pressure gradient. We have 102 millimeters here, 40 millimeters there. Guess what? Oxygen flows from the alveolus into the capillary. But oxygen needs to bind, most of it, a vast majority of oxygen needs to bind to hemoglobin. So it's really not much in the plasma itself. There's a tiny little bit, a few percentage oxygen that dissolves in plasma itself. Vast majority of it is bound to hemoglobin. We're going to talk about that in a minute. I should probably move me because I don't even know where to put me now, so I'm not in the way of the words. All right. Now, carbon dioxide. So we look at the other side of this equation, right? Blood flow from the right ventricle. Here's the partial pressure of carbon dioxide. It's about 45 millimeters of mercury at this point. And that's waste product. Now, CO2 travels in various forms that we're going to talk a lot about, the chemistry of that. And the partial pressure of CO2 in your alveolus is 40 millimeters of mercury. Now, that might be higher than you think, but there are, again, various reasons for that, so you're going to have to accept that number for the time being. But there's still a gradient. So 45 to 40, so CO2 wants to flow, wants to diffuse along its pressure gradient, partial pressure gradient. And so, of course, it's going to go into the alveolus. Now, this gradient is not huge, but it's still a gradient. So it is going to happen that way. It's going to flow. The interesting thing, though, is that carbon dioxide is useful for other purposes in your blood other than just a waste product that you get rid of. It serves, and when we get to the chemistry of it, it serves as a buffer in your blood to buffer the pH of your blood. And so it's useful for other things. Oxygen is pretty much, well, I shouldn't say useless, but there's not much you can do with oxygen other than use it in the generation of ATP. Other than that, there's not a lot of uses that your body has for O2, but it does have more uses for CO2. All right, now, yeah, here we go again, I'm in the way. Yet again. Story of my life. Okay, gas transport. Blood transports O2 and CO2 between the lungs and body cells. All right, you already know that. Gas enters blood. It dissolves in the plasma or chemically combines. So it dissolves in the plasma, that's mainly CO2. Yes, a little O2. Or chemically combines with other substances. Of course, oxygen goes to hemoglobin. Carbon dioxide can also bind to hemoglobin, but there are rules around that. Okay, so let's talk about oxygen first. As I said, oxygen travels around your blood two different ways. I've already said almost all the oxygen, 98 to 99% of the oxygen that you breathe in, once it gets into your blood, it is bound to hemoglobin. At the iron, right, at the binding site. In the middle of the heme group where the iron is, that's where it binds. The other 1 to 2% is dissolved in blood plasma. O2 loosely binds to the iron. Now loosely, this word loosely, you have to think, what do you want oxygen to do? You want the oxygen to bind to hemoglobin where there is a lot of oxygen in the lungs. But then when that red blood cell, when the hemoglobin gets down to body tissues that need the oxygen, you want the hemoglobin to let go of the oxygen. It turns out that hemoglobin is pretty good at that. And so we're going to talk about these principles. But that's what you want it to do. All right, so the iron binds to the O2, and you form this thing called oxyhemoglobin. And technically speaking, you either have oxyhemoglobin or deoxyhemoglobin. You know, there's nothing really, there's no such, I mean, I'll say there's really no such thing as hemoglobin. Yeah, of course it is hemoglobin. But functionally speaking, it's either got oxygen bound to it or it doesn't. So it's either oxyhemoglobin or deoxyhemoglobin. There's another compound we're going to get to in a minute. And remember, hemoglobin has 4 subunits. One molecule of hemoglobin has 4 subunits, and each one of those subunits can hold one O2 molecule. Right, so it can hold 4 O2 molecules. 4 oxygen molecules. One molecule of hemoglobin. Right, and this is true. The chemical bonds between oxygen and hemoglobin are relatively unstable. And at first you think, wait a minute, well, unstable. You want them to be unstable. You don't want hemoglobin to love oxygen and hang on to it forever, because then it would. It does do that to carbon monoxide. Carbon monoxide has a very strong affinity for that iron, and so this is called carbon monoxide poisoning. It never lets go. Once carbon monoxide binds to that iron, it doesn't let go. That's why we call that carbon monoxide poisoning, because it acts as a poison. And it does not allow oxygen to bind. So once all your hemoglobins are filled up with carbon monoxide, you're done. Okay, so factors which increase the release of O2. I'm also going to get into the functionality here. Why should oxygen want to be released, or why should hemoglobin let go of oxygen in these particular situations? All right, if you have a decrease in partial pressure of O2, hemoglobin wants to let go of oxygen. Where does that happen? A decrease in the partial pressure of O2, it happens in body tissues. Well, that's where you want hemoglobin to let go of oxygen. Okay, number 2 here, increase in partial pressure of carbon dioxide. Where are you going to get an increase in the partial pressure of carbon dioxide, the concentration of carbon dioxide? In active tissues. When they're actively metabolizing, they're producing carbon dioxide. Okay. That means they're using the oxygen to go through the process of making ATP. They need more oxygen then. That's what you want hemoglobin to do, is to let go of the oxygen so it can keep that process going. Increase in acidity. Remember when we were talking about muscle, and you're working your muscles real fast, and you're trying to generate energy, and at some point you can't generate enough energy. You can't generate enough ATP going through the oxidative pathways. So you go through the anaerobic pathways, and the anaerobic pathways result in lactic acid. Increase in acidity means that tissue does not have enough oxygen to continue to generate enough ATP to do what it's trying to do. So again, you want hemoglobin. You would like hemoglobin to let go of oxygen in those areas where there's an increase in acidity. That means the pH goes down. Remember that weird thing about how the pH scale works. Lower numbers are more acidic. And an increase in temperature. It's the same thing. When you are walking or running or exercising, your muscles are generating heat. Remember, that's how you generate heat for the body. That's how you make yourself a homeotherm. You are making your own body heat. When that heat rises, that means you're using up oxygen to make ATP. You're running out of that stuff. You're generating heat. If you're generating more heat, it means you need more oxygen. You want hemoglobin to let go of oxygen in those cases. So I want you to understand, this is not just like random, where we didn't just measure these things and say, oh yeah, okay, I measure it. Okay, I'm going to memorize all those things. I want you to think about the rationale behind this. What is your body thinking? Well, it's thinking it needs oxygen because of all these reasons. So the released O2 moves from the blood into the tissues. Concentration gradient. 75% of the O2 remains bound to the hemoglobin in venous blood to ensure safe CO2 levels and pH. So not all of your O2 that's bound to hemoglobin lets go. It's not like 100% of the hemoglobins are bound to oxygen in your lungs, and then they go to your working muscles and there's 0% oxygen bound to hemoglobin. It doesn't work that way. So you get down to about 75%. That's what deoxyhemoglobin is. When we say blood is deoxygenated, what we mean is it's less oxygenated. Okay, now we can talk about this curve. This curve is called the, obviously you can see the hemoglobin saturation curve, or the oxygen. It's also called the oxygen dissociation curve. Or you can think of it in the reverse, the oxygen association curve. What it means is, I'm gonna move me again. Where can I not be in the way? I guess it's okay here. All right. What this curve tells you is what I already told you and what you already know intuitively. When you're in the lungs, hemoglobin, there's a lot of oxygen in your lungs at the alveoli. Hemoglobin comes in and it gets to fill up, right? It's going to the grocery store. The grocery store is oxygen, so the hemoglobin says, great, bring it on, fill me up. So where there is a lot of oxygen, hemoglobin wants to bind that oxygen. And so that's what this is, the partial pressure of oxygen here, partial pressure of oxygen in millimeters of mercury. What did I say in the alveolus? It is 104. So it's right about here. So the partial pressure of oxygen in your alveolus is 104 millimeters of mercury. That's a lot. Guess what? If I look at about 104 and I draw a line straight up, straight up, straight up, straight up, straight up, straight up, bam. What do I got? I come to a point that says 100. 100 what? 100%. 100% of hemoglobin. It's not actually quite 100%. It's about 98%, 99% maybe. But for argument's sake, we'll say, okay, all of my hemoglobin is bound where there is a lot of oxygen. I want that oxygen on hemoglobin. Boom. Okay. Done. Problem solved. Great. Where there is a lot of oxygen, a lot of it is bound to hemoglobin. Excellent. All right. Now I got to take it to the tissues. What's the partial pressure of oxygen at working tissues? It was 40. 40 milliliters. Come down here is 40. Okay, at 40. What do? I go up, 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 up. 75%. So 75% of the hemoglobin molecules have oxygen bound to them. So we consider that a deoxygenated situation. Well, it's not really deoxygenated, it's just less oxygenated. And 75% really isn't, that's really not enough. You could live that way for a while, but eventually your tissues that need more oxygen would start to starve for oxygen, and so that's no way to live. But you can see, right? Oxygen, hemoglobin, let's say it this way, hemoglobin lets go of oxygen when the partial pressure of oxygen is lower. Where does that happen? That happens in body tissues. Hemoglobin binds a lot of oxygen, nearly 100%, where there is plenty of oxygen. Where's that? In the lungs, right here. That's what this curve is telling you. Now you might say, you might think, oh, shouldn't it be a straight line? Yeah, like it could have been a straight line, but when this was measured more than 100 years ago, we didn't know what kind of line it was. It just turns out that this is what we call a sigmoidal curve, an S-shaped curve, right? So it's shaped like an S. And so it means at various points in this curve, there's a steeper gradient. At various points, there's a less steep gradient. It's just telling you the saturation status of hemoglobin at any given concentration or partial pressure, in this case, partial pressure of oxygen. If there's a lot of oxygen, the hemoglobin's full up. If there's not as much oxygen, the hemoglobin lets go of oxygen. That's what you want. That's what you want it to do. So it says the hemoglobin is completely saturated in the systemic arteries due to the high partial pressure of oxygen. But it releases oxygen to the body cells due to the lower partial pressure of oxygen. Great, that's what I want. So hemoglobin does what I want. Well, of course, you know, it does what I want, but of course it's there, so it must be doing what I want. So anyway, there it is. That's what it's doing. Okay, this curve tells you that. This is an oxygen dissociation curve or hemoglobin saturation curve. Same thing. Okay. Now, transport and dissociation. Okay, you're in the alveolus up here. Gotta move again. I'll put me down here now. So here's an alveolus. Partial pressure of oxygen, 104 millimeters of mercury. Great. Diffuses across to cells. That partial pressure oxygen here is 40 millimeters. Nice gradient. Excellent. It diffuses. Goes on to hemoglobin. Goes through left side of the heart. On to the rest of the body. Good. Here's my hemoglobin. Now I get to the tissues that have a partial pressure of 40 millimeters mercury oxygen. Excellent. Hemoglobin lets go of oxygen. It diffuses by its concentration gradient because you had 100, we're going to say it's still 104 by the time you get to here, 104 millimeters of mercury, partial pressure here. It diffuses into the cells. That's what you want it to do. Great. Excellent. Circulates around, goes to the right side of the heart, back to the lungs, picks up more, on and on, round and round and round you go. Perfect. That's exactly what you want. It's true, hemoglobin still is about 75% saturated in venous blood. And yet we call that deoxygenated blood. It's just less oxygenated. Okay, now this curve, this saturation curve, the affinity of hemoglobin for oxygen changes in different situations. I'll put me in the middle here. Right in the middle of everything. Yeah. Okay, situation 1. Here's the first situation up here. As the partial pressure of carbon dioxide increases, so does the amount of oxygen released from oxyhemoglobin. Where would the partial pressure of CO2 increase? It would increase in working tissues because they are going through the process of making ATP, bioenergetics. In that process, you generate CO2. So, partial pressure of CO2 is going to increase around tissues that are actively metabolizing. In those same places, oxyhemoglobin is going to release the oxygen to those working tissues. Excellent. It turns out that as you increase the partial pressure of CO2, so if it's 20 millimeters of mercury, that's not a very great amount. That's not a very good concentration of CO2. 40 millimeters of mercury is about normal, average for many body tissues. 80 millimeters of mercury of partial pressure of CO2 means these are like muscles that you're using when you run. The change in this curve, what we call it a right shift. The right shift in this curve tells you that hemoglobin is going to let go of oxygen more easily in those circumstances. But this is exactly what you want. If this is considered the amount of CO2 that is in your working thigh muscle as you're running, you want more oxygen to get to those tissues. This higher concentration of carbon dioxide allows oxygen to be released more easily from hemoglobin. It's what you want. Okay, situation 2. As blood pH decreases, remember that means the acidity increases. So, if normal pH is 7.35, if it decreases to 7.2 or 7.1, which is pretty acidic actually for blood, but if it did that, oxyhemoglobin releases oxygen more easily. Again, it's another right shift. If the pH is 7.6, that's more alkaline. Oxyhemoglobin is going to hang on to the oxygen more firmly. And then as we go to the right on this curve, as we go in this direction, this oxyhemoglobin here at a pH of 7.2 is more likely to give up its oxygen than the hemoglobin at a pH of 7.4 or 7.6. Now you look at these things and you may say, well, that's not a big difference. But it's enough of a difference. You have to appreciate that that is enough of a difference to make a difference in hemoglobin letting go of oxygen. Situation 3. Situation 3 is here as blood temperature increases, the amount of oxygen released from oxyhemoglobin increases. Okay, again, working muscles. Now this is just the easiest situation to explain. Of course, this happens in anywhere in the body where temperature increases, but it's easiest to understand when you're talking about muscles, because muscles generate their own heat as they're metabolizing ATP. And so you can easily see how it would increase the temperature of the muscle. And again, another right shift. As you shift the curve to the right, you are allowing hemoglobin to let go of oxygen more easily. So it's called a right shift again. As it goes to the right, hemoglobin lets go of oxygen more easily. If it goes to the left, hemoglobin hangs on to oxygen a little bit more firmly. Okay, this curve is a combination of all of those curves. So I guess I'll just put me down here somewhere. This is a combination of all the curves. So the blue line is considered kind of the average, normal, everyday situation. Okay. The red curve is a right-shifted curve. When does that happen? That happens when pH goes down. That means it becomes more acidic. Forget this stuff called DPG. That's diphosphoglyceride. Don't worry about what that is. It's a metabolic byproduct of anaerobic metabolism. We're not going to worry about that. So a decrease in pH, if it becomes more acidic, you get a right shift. If you have an increase in temperature, you get a right shift. Right shift means hemoglobin lets go of its oxygen more easily. This has a name. This is called the Bohr effect, B-O-H-R, the Bohr effect, when concentration of carbon dioxide goes up, and any time that happens in the blood, you can count on the pH of the blood going down. That means it becomes more acidic. More carbon dioxide leads to a more acid blood. And the Bohr effect guarantees that under those situations, hemoglobin will let go of oxygen more easily. On the other hand, the other side of this curve, the green line indicates that hemoglobin is going to hang on to oxygen more readily. That happens when the pH goes up, so things become more alkaline, or when the temperature goes down. That also has a name. That's called the Haldane effect. I've looked at some of the test questions and I haven't seen these names anywhere. This particular graph has that on there. So the Haldane effect. What that means is this will tend to happen in the lungs, where there is a lot of oxygen already, and we're going to find out that hemoglobin can carry carbon dioxide in the blood. That's one way that carbon dioxide shuttles around. But it can only carry either oxygen or carbon dioxide. When it's carrying oxygen, it displaces the carbon dioxide from hemoglobin. So this letter combination HB, that's hemoglobin. That stands for hemoglobin. So oxygen displaces carbon dioxide from hemoglobin when there is a lot of oxygen. That's what we want, right? We don't want hemoglobin carrying carbon dioxide all over the place. We want the carbon dioxide to get out of the way when there's a lot of O2 around. But we want the O2 to jump off the hemoglobin where there is not a lot of O2 around, or when there's a lot of carbon dioxide around. Working tissues. So this is a summary graph of all of the stuff, all the situations. Okay, we talked about oxygen. In some ways, oxygen is a little simpler because hemoglobin does the grunt work there. Carbon dioxide is more complicated because the chemistry of carbon dioxide allows it to be more complicated. It's more, but it's also more versatile. I think that's a better way to think of it, rather than complicated. Okay, cellular metabolism generates carbon dioxide. You already know that. We've went through this before. CO2 diffuses into capillaries. Tissues have a higher partial pressure of carbon dioxide than capillaries do. Why? Tissues are metabolizing. Metabolism generates CO2 in the cell. Becomes a higher in concentration. The capillary is going by and has a lower concentration of carbon dioxide. Into the capillary it goes. Now there's three ways that you can transport that carbon dioxide. Carbon dioxide can be dissolved right in plasma, just as a gas. So you're carbonated, essentially, right? Go to your fridge, get a pop. Carbonated beverage has CO2 dissolved in it. So do you, but not a lot. Second way, CO2 binds to hemoglobin. I've mentioned that before. When it does bind to hemoglobin, it does not bind at the iron. It binds on one of the side groups, one of the amino acids that makes up one of the chains of the hemoglobin molecule. So again, hemoglobin can carry 4 carbon dioxide molecules that way. If it is carrying carbon dioxide, it is called carbaminohemoglobin. Right? So the carb for carbon dioxide. Amino means this thing is attached to an amino group on the hemoglobin. So we call it carbaminohemoglobin. Remember before, the last graph that I showed you, carbaminohemoglobin will not allow oxygen to bind to it. So it will compete with oxygen. But where would this happen? This would happen at tissues where there is a high partial pressure of carbon dioxide. All right, way number 3, and this is by far the majority, part of a bicarbonate ion. The majority is transported this way. 60-70% or more is transported in the blood as this compound. This compound is called carbonic acid. So carbon dioxide plus water. You got water in plasma. And this is an enzymatic reaction. So there's an enzyme that's not being mentioned here. And this is a double-headed arrow. So you have to remember that carbon dioxide plus water plus an enzyme called carbonic anhydrase. Carbonic anhydrase converts CO2 and H2O into H2CO3. That is carbonic acid. But it can reverse the reaction. So it can take H2CO3, it can take carbonic acid and turn it into carbon dioxide and water. That's going to be really important in just a minute. So it's a reversible reaction. Carbonic anhydrase can move this equation in either direction. If it moves it towards H2CO3, carbonic acid, it's an acid because the H plus, and the H plus is a proton, as it always is. So H plus is the acidic part of carbonic acid. Then you're left over with this other thing, HCO3. HCO3 minus is called the bicarbonate ion. This is a wonderful buffer. So your body uses it as a buffer. So carbon dioxide doesn't just have to be exhaled. It can be used for other purposes in your blood. All right, one more time, I got to go through this because this is important, because I almost guarantee you're going to have a test question on this. CO2 combined with H2O and the enzyme carbonic anhydrase creates an acid called carbonic acid. Carbonic acid will dissociate almost immediately into H plus HCO3 minus, the bicarbonate ion. Or it can go back the other way. So carbonic anhydrase works right here at that double-headed arrow. It can make carbonic acid, or it can turn carbonic acid into CO2 and H2O. Right, so move me again. I'll move myself over here this time. Okay, tissue cell. Tissue cell, you got to know where you are in the body. So you're in the tissue. Working muscles, kidney cells, brain cells, whatever, wherever you are. That tissue is metabolizing, right? It is generating CO2 because it's undergoing normal metabolism. All right? In the tissue, that means it creates a partial pressure of oxygen of 45 millimeters of mercury. That's normal. The blood that's flowing by that cell has a partial pressure of oxygen of 40 millimeters of mercury. Guess what? Pressure gradient. CO2 flows into that cell, or into the capillary. Now, what does it do? Some of it dissolves directly in the plasma. Some of it combines with hemoglobin to form carbaminohemoglobin. Some of it gets converted to carbonic acid, dissociates, and you get HCO3, the bicarb ion. That is often used as a buffer in the bloodstream. Now this H plus that's left over combines with hemoglobin and denies oxygen a place to bind. It actually is a competitor of oxygen. So in this area, in the tissues area, you're not going to get hemoglobin sucking up oxygen just for fun. Nope, you're going to get competition with oxygen so that the oxygen goes from the hemoglobin into the working cells. And then it gets competition because there's a little bit more of an acidic environment here. You know, and so, as I say, we're talking about a 0.05 to maybe 0.1 pH difference in these tissues. It's not a lot, but it's enough. Right, so there's the three ways as bicarb ions dissolved in plasma or bound to hemoglobin. That's at the tissue. Next up. Okay, we move forward. All right, now there is a thing that happens. So you know that we form carbonic acid, and that dissociates into H plus HCO3 minus. You got to keep things in context here because the HCO3 minus has a negative charge to it. And I showed you that it goes out into the plasma and becomes a buffer. Isn't that nice? Yeah, well, then your red blood cell has lost a negative charge. You can't charge the red blood cell. So you have to replace the negative charge that it loses with something else. Conveniently, there's lots of chloride around that also has a negative charge. So in terms of the charge that you're losing because of the bicarbonate ion, you can gain or replace it. I probably should say it that way. You replace that negative charge with a chloride ion. This has a name. This is called a chloride shift. Right? Negatively charged bicarbs diffuse out of the red blood cell. Chloride ions from the plasma diffuse into those cells. This maintains electrical neutrality in the red blood cell. That's important that does that. It's called the chloride shift. Okay, now we were just in the body tissues. Okay, we've got more carbon dioxide there. Some carbon dioxide is bound to hemoglobin, carbaminohemoglobin. Some of it is bicarbonate ion in the blood. Some of it is straight up dissolved. CO2 is dissolved right in the blood. That's in body tissues. Okay, circulation continues. Now we get back to the lungs. We're back in the lungs again. Now we're going to look at what happens to CO2. We looked at oxygen before. Here's the alveolus, thin membranes. Here's the blood coming along. Right? CO2 is dissolved in the plasma. The CO2 is at a partial pressure of 45 millimeters of mercury, as we saw before. So the CO2 that is directly dissolved in plasma directly transfers across these membranes into the alveolus. Okay, so CO2 is CO2 in the blood as a gas. It diffuses across as a gas into the alveolus. Great. Okay, step one. The next thing. Here's my HCO3, my bicarbonate ion. Now it re-enters the red blood cell, and it combines with the H+, the proton that it left behind out in the body tissue. When it recombines, it forms carbonic acid, which carbonic anhydrase, the enzyme, now converts from carbonic acid into CO2 and H2O. H2O is fine. We got lots of H2O. That just stays in the red blood cell or goes out into the blood plasma. The CO2 now can diffuse across as a gas. All right, so that's the second way that carbon dioxide is carried around. Third way, remember carbaminohemoglobin. That carbon dioxide was directly attached to the hemoglobin, to an amino acid of the hemoglobin. Well, hemoglobin lets it go. And so now you have, again, CO2, and that CO2 is dissolved in the plasma. And again, it follows its pressure gradient. It's a higher pressure in the plasma here, lower pressure in the alveolus. So this is how you get gaseous CO2 in your alveoli. It's either straight CO2 as it is in the plasma. It is either reconverted back into CO2 and water by carbonic anhydrase, CO2 gas, or the CO2 that was hanging on to hemoglobin gets released. Now it's a gas, CO2, boom, across it goes. That's how you get it. So CO2 diffuses from the blood to the alveoli, and then it's exhaled. So this is the same reaction down here. It's just written in reverse. But it's still carbonic anhydrase works on this double-headed arrow. This side of it, this side of the equation, happens automatically. The hydrogen ion is automatically let go from the bicarbonate ion in water. But once they recombine into carbonic acid, carbonic anhydrase converts it to CO2 and H2O. So I told you that that's a reversible reaction, and depending on where you're in the body, where you are in the body, you can go either way with that reaction depending on what you want to do with the carbon dioxide. So this is a good point to say, when you have more carbon dioxide, when you have a buildup of carbon dioxide for any reason, whatever the reason might be, that area of the body is going to be more acidic. That means the pH will be lower. Now it might not be very much lower. It might be, instead of 7.35, it might be 7.25. Well, that's more acidic. It could be 7.15. If it gets much below 7.0, your life is at risk. And you would think, well, gee, that's not very much. Well, it's enough. It's enough to create a life-threatening situation. Okay, gotta move yet again. All right, I'll just go down here this time. Okay, so here it is. Here's the sum total, right? Oxygen 1 to 2% is dissolved in the plasma. 98 to 99% of the oxygen is attached to hemoglobin in the form of oxyhemoglobin. Carbon dioxide, 7% dissolves in plasma as the gas, CO2. So you are carbonated. 23% of it combines with hemoglobin and forms carbaminohemoglobin. It means about 70% forms carbonic acid. Then dissociates and has hydrogen ions and bicarb ions. There you go. So that's CO2. And I believe that's it. Yeah. Right, so thus ends the respiratory system lecture and information that you have to know. Make sure when you're studying, when you're thinking about what's going on in the body, in the respiratory system, between oxygen and carbon dioxide, think about where you are in the body and what's happening in those surrounding tissues. What do you need to happen? It turns out that's exactly what does happen. But you have to know the names, the specific names of the situation that is happening wherever you are. and you have to know more of the particulars about those things. But when you have a lot of oxygen, hemoglobin is going to hang on to oxygen. Great. When you don't have a lot of oxygen in body tissues, hemoglobin will let go of oxygen. Great. Hemoglobin can carry some of the carbon dioxide, some of it's dissolved in your blood, some of it's converted to carbonic acid. Remember, carbonic anhydrase is reversible. It can go either way with that reaction. It creates CO2 and water in the lungs to get rid of CO2, or it can be used as a buffer in the blood to maintain a very, very tight control of the pH of the blood. The pH of the blood is 7.35 to 7.45. If it is very far outside, above or below that, your life is in danger. It has to be very tightly controlled. So when it gets to 7.25, 7.2, we start to get a little nervous. And as I say, even though it doesn't seem like a huge difference, trust me, it is, and you need to recalibrate your internal sensors to think that is a huge difference. Now you're going to say, yeah, but what about the stomach? Yeah, well, the stomach is the stomach. pH of 2, very, very acidic. Keep all that stuff inside the stomach. Everybody's fine. This is why stomach injuries, things that open the stomach up and allow gastric juices to flow elsewhere, that's very problematic, and that really causes a lot of problems if you have that kind of an injury. So don't get that kind of injury. Okay, I'm gonna put this out on YouTube, and you can watch it at your leisure. Thanks for your attention. See you later.